Okay, this is the 25th lecture. I'm finally going to show you a non-trivial example of the three uses of these things we call representations, irreducible representations actually. And we're doing it for both the rotation in 3, which is the one that's most familiar to us as we walk through a three-dimensional real space, but it's also taking care of the unitary group. That's the group that we've been using as two-dimensional oscillator symmetry. And there are three applications that you should know that all symmetry analysis can do for you, this advanced Fourier analysis can do for you. The first one is to make you a wave function. Actually, in many cases, an eigenfunction, but something that's closer to an eigenfunction than what you start with, which is something that's localized. So this is the projection operator business, where there are two sides to the projection operator, and that comes up in this Mach principle. And the use of those two sides in a neat way really shows with respect to rotational problems that we'll talk about midway through this lecture. And the second thing is that the irreducible representations provide you with transformation matrices. Now this second one is the one that most people think is the only thing that these D functions do. But they certainly do that. And we need to discuss that not only for the standard transformations of vectors and tensors, but also situations where you have really large angular momentum, much larger than 1/2, 1, or 2 that spinors, vectors, and tensors have respectively. And then finally, the third thing that I would point out is that you also can make Hamiltonians out of these representations. And in particular, tensor operator Hamiltonians. So this will be our first introduction to that in this course. And we'll be spending the last few lectures talking about things that they do and how other ways to make them. And we haven't talked about so far is Clebsch-Gordan coefficients, and that comes up in very beautiful ways with respect to these. In any case, the things that we're making here are called multiple functions or operators. And we're doing a multiple expansion of a very simple Hamiltonian, the simplest second-order Hamiltonian of rotation. And in this case, a rotation of an asymmetric rotor and a symmetric rotor. Here's where the symmetry really shows itself. And I'm talking about the Mach-Mach symmetry, inside and out. But this suggests a solution using geometry, which we call the rotational energy surface. And I'm gonna, at the end of the lecture, show examples of that. And then I hope we get to a point where I can give you a sketch of the symmetry analysis in modern electronic, vibrational, and rotational spectroscopy, a lot of which includes vibration and electronic structure of solids. The solids don't rotate, so they get to avoid that problem. We are taking care of the rotation very elegantly in what comes all the way through this lecture. And I'll give you an example of rho vibrational spectroscopy, a way to view it geometrically. If we have time, we'll take on the rho vibrational analysis a little bit of the asymmetric type. But that's probably going to be mostly for the 26th lecture. So let's get started here. This is a listing of websites that are still pretty much the same as far as I can tell as they were a year ago. So you can make use of those to get a hold of the notes for this lecture. And you'll need them because we're going to have a lot of small type that might be hard to read on a video. So take advantage of that. So let's do the number one thing here first. Yes, TC.
There's a link in the info section for the YouTube site or page in which you find this on. If you look in the info section, it shows a link to those PDFs.
Okay, that's good. The more the merrier for portals to this, because I find when I want to look something up, I suddenly read, okay, what's the pathway? And it's good to have something like that. Fortunately, we can just Google my name sometimes and get stuff, but it'd be nicer to go directly to the multiple things that are on this site. Okay, here's where we use the projection operator in conjunction with the representation. And remember, don't forget the star when you do that, the complex conjugate. E to the minus ikx in the case of plane waves that we introduced this with. So this is something we saw last time. In fact, we derived last time the formula, the binomial expansion, basically of the spinors. The spin a half, notice these are cosines of angles over 2, which we immediately convert in order to make it look like something that we are more familiar with. But still, this is the very fundamental, but not quite as fundamental as a spinor, but the vector representation of R3 really could be called the fundamental representation of R3. And that's what we're spitting out here. With all 3 Euler angles, the angle associated with the internal frame, the so-called phase or gauge, is riding along on the sort of right-hand side of the factors there, and the alpha is the, shall we say, the dynamic phase in the case of the spinors, but here it's sitting there with 3 components which show up in this matrix. Anyway, converting that and also doing something else, a notational switch from alpha, the azimuthal angle of Euler, to phi, which is most people's idea of a symbol for the polar azimuth, and then the actual polar co-elevation, theta, that rhymes with beta, is being done right here. The basic idea, if you recall from what we did last time, is that the center column of this matrix are the spherical harmonics, which you often struggle with producing by ordinary power series methods that have lived since the 1800s. This is very elegant in getting a complete formula for all of those things, plus some more, much more. The whole matrix is filled with wave functions, as we're going to talk about. But here are the usual dipole wave functions gotten by taking the complex conjugation of d, that's the wave function yl in there. So yl star is the representation matrix that's sitting in this. You notice the minus sign on e to the I phi here in alpha. So we've just turned alpha to phi and beta to theta in writing out a formula that you find in any textbook that uses standard conventions of phase for orbital wave functions. So here they are again, but this time with a star on the d and making the y. So I have a plus I phi here. And this is something we had a little bit of trouble last time getting the signs right. If you just read across right here, x plus I, y, that's the matrix with a minus sign. -1, minus I, and 0 is that. Then this one right here is just a 0, 0, 1 for the z component, which is the third column of this transformation matrix. In any case, this is a transformation matrix that converts you from the subgroup chain of a cyclic group that would have complex waves, things that has a C-type symmetry and has current, and something flowing, so to speak, to standing waves, the x, y, and z standing waves that we call our ordinary vector. That is, the things that transform, like cosine, sine, minus sine, sine, talk about the y axis, axis, axial rotation, or the z one, that's the most familiar, is that x and y components are just a cosine, minus sine, sine, cosine, and then nothing happens to the z component. But if you put all 3 of these together, with this transformation, you get the thing that we worked a little bit to get in the Euler description back when we were talking about spinors in lecture 13 or lecture 12. Okay, anyway, here's pictures of them. This is the real P standing waves, X, Y, and Z. There's Z, two spheres sitting on top of each other, one with a negative phase, the other with a positive phase, then something doing the same thing on the y-axis and something doing that on the x-axis. Here's what they look like if they're squared. They get a little elongated, sort of egg-shaped. Spheres turn into eggs. Or if you use just the straight angular momentum states, that's what their squares look like. Now we have animations and things that we could make, right, for these x plus I, y wave functions. But the squares sit there. They don't move. But they have a little arrow on it to indicate which one's right-handed and which one's left-handed. Same thing with angular momentum 2. Now here's a tensor representation, so-called because it's made out of x squared, xy, xz, and so forth. And this is that formula giving all of those. Again, the spherical harmonics are sitting in the center, all phased and normalized. That's what group theory does for you automatically. It's very powerful. And not only do we get those, but we get all of these other wave functions that have to do with a quantum rotor. And that's what we're going to discuss today, is some examples of that for not just angular momentum 2, but very high angular momentum. In any case, here are the D stars, which are the spherical harmonics, here with the second index set equal to 0, and that's what this column is. This is a column for n equals 0, n being the quantum number associated with a nuclear frame, that's the way I remember the n, of a rotor that we'll be talking about later on. Same notational shift, alpha and beta, for the laboratory polar coordinates is being used here. So you have a bunch of quadratic functions of x, y, and z, divided by r squared, which makes them dimensionless. And if you choose to not make them dimensionless, then you have something called a multipole function. R to the k times yk cubed is just multiplying by radius to whatever power the rank of this tensor is. In this case, it's a 2 for just exactly the angular momentum. So there are 5 states shown with their waves. They're standing waves. We've done sums and differences between these to make xz, xy, and yz waves according to these other formulas that we just put up here. And then there's x squared minus y squared right here, which is just this thing turned so that it now has antinodes on the Cartesian axes, whereas all of these things are avoiding all 3 of the Cartesian axes. And then finally this one right here, which has 0 angular momentum around the z-axis, and therefore it's just hugging the z-axis. This one's avoiding the z-axis, but it's kind of chummy with the xy axes. And then these things are just avoiding the x-axis themselves. Now that avoidance or attraction to axes is really important for analyzing, as I mentioned, the materials that are going on under our feet here in the laboratory of Jack Kalin. And he's able to make things that play with combinations of these to just move the charge off an axis or onto an axis in order to make various physical properties of current and magnetism and such like that occur.
What does zero represent in
this one?
Yeah.
Zero is what represents this whole column, and for us, for the molecular wave function, it indicates that the body frame, the body Z frame, wherever that has no angular momentum. So it would have a wave function, something like that. It would have a wave function that grabbed that axis. You see, would favor that axis, not try to avoid it. So yeah, we'll get to what that zero is. But basically, you've got to realize that this is a matrix of some component 2, 1, 0, minus 1, minus 2. That's the m equal 1, n equal 1, 2, 1, 0, minus 1, minus 2, and then m equal to 1, you see, n equal to 2, 1, 0, minus. These are all components that have addresses of m and n. Okay, now I put q here. We had just been showing this thing with m's. That's actually what I'm writing right there. M equal 2, m equal 1, m equals 0, minus 1, minus 2. You see the y, you know it's a d, but with 0 for the n, which means center column. It's really a wonderful structure when you play the two dimensions against each other. And that's what we're going to really talk about here. So these are great for atomic physics, not so great for molecular physics. They're just a very small part of what a molecule. This thing's only got 5 degrees of freedom. This is 25. If you're talking about a rotor, a quantum version of this guy right here, this little thing can whip around here in all alphas and betas and gammas. It's got a quantum wave function associated with each setting value of a complex, in general complex, D function, Mn of alpha, beta, gamma. So that's what we're really talking about here.
Is there a diagonal representation of the D matrix?
Well, any of these matrices by themselves can be reduced to a diagonal. And it will be reduced depending on what the Euler angles are. If it's just alpha, it'll be reduced to e to the I 2 times alpha, 1 times alpha, 0 times alpha, minus 1 times alpha, minus 2 times alpha for that case.
So what are the significance of this eigenvalues? Do they have any significance?
Well, if it's alpha, it's the coherent phase of some sort of oscillation of the wave. It literally is the classical phase if you're talking about precession. But if it's gamma, if you were reading the thing this way, you see, their functions are that go with the n equals 0, then that's something in the laboratory that has, well, no 0 phase, but any of the others would be the overall phase. The gamma is the gauge of this rotor's wave function. It's nice that G, Greek G, refers to gauge, but that's what it is. It's the overall phase. Now we saw this for the two-state system. Alpha and beta determined the orientation of the Rabi spin, quasi-spin, or actual spin vector, right? They were polar coordinates of that. The gamma is the twist. That's this dial right here that holds the ball. That's the azimuth for people in the body frame, you see. They see the alpha as your gauge. You're the outside person. They have their gamma as their azimuth. Then they both of them share the beta angle right there as a polar angle. One of them uses it positively, the other uses it negatively. So all of this stuff, this Mach-Mach principle, is part of our quantum lore that really needs to be taken seriously if you really want to be doing things smoothly. Okay, I'm going to move on here just to show them again. These are standing waves. Those are moving wave distributions for angular momentum. M equal 2, M equal 1, and M equals 0 is just a square of that thing. And now they all have along them no spheres here anymore, even for the amplitude, but certainly for the square. They're getting very long. Now I'd like to show something here just briefly. And that's the center component of the matrix. This guy. Every matrix that has an integral quantum number 0, 1, 2, 3, 4, 5. Not halves. Halves, you don't have a center. But the integral ones, you do have a center here. That's a Legendre polynomial P, J, or L. You recognize it?
Yeah, 2.
Okay?
T2.
And it would be this guy. P2 cosine of theta is that guy. Plotted. Now our old friend P1 of cosine, that's just a z, right? That's what we would call a dipole, right? Now if you take a dipole, make a copy of it and change its sign, and then lay it down next to the old one, okay? So that, actually it would be laying it down this way, then I get 2 charges here and plus there. 2 negative charges here and plus there. That's a elementary quadrupole, one-dimensional quadrupole. Okay? Now what I did was I took the derivative of this to get that. Now what's a derivative? It's f of x plus f of x, or I should say f of x plus delta x, function of x plus delta x, minus f of x, right? Divided by delta x. Well, forget the delta x, we'll scale the thing later on. But basically, to get this one, I take a derivative. I say, I take this thing and move f of x plus delta x, and then I add just f of x with a minus sign. So that makes me a dipole. Then I get a quadrupole. Then I take this thing, copy it with a sign change. In this case, I push down and add it to this. I get this and this and this and this. And end up with a Pascal triangle of plus and minus charges. Whose, if I take this thing and microscopically put it down inside there, that's the field it makes. That's its potential function. This should be taught in every E&M class. This really lets you see what multipolarity is. But remember, it's just a center function of our D matrix. All normalized and phased and everything perfectly. There's not much phases on the center because alpha and gamma get to have no component. Okay, so this is something worth thinking about, but we'll just pass interest to it. Okay, now this Mach thing, where does that play a role here and why? Let's review that. We've been through this in lecture 14 with respect to the finite groups. Now we're talking about all possible rotations, so this is really making it apply to everything in the R3 and U2 world, but I claim it's good for any symmetry problem, particularly permutational ones. But we have a lab-fixed set of operators, and there's the victim, the quantum object, is inside there. The lab is classical lab. Where classical lab doesn't keep very good track of the phases of its little devices, which are very massive and large and complicated compared to, presumably, a quantum object, you say. So we tend to think of them as just very different from us. But the idea is that you take this thing, and stop being so chauvinistic, and say, hey, this could be, you can imagine that the wave has an existence too, that it could think about moving itself with operators that are attached to it. Just like we have operators attached to us. We think that's, of course, we're the ones that do the operations. You're just the victim. But here's the victim now doing its own rotations. So we really have two groups here that commute with each other. That's really, I think, an important thing. And those two groups are related by this, what I call the Mach principle. And that is, if you start at 0, you'll get the same relative position by applying a laboratory operator to an initial original state, as it would be if the body were to somehow apply the inverse operator to the original setting. Now this is for one state only, a unit state, a original state only. You cannot equate this operator with this. If you did, you get in trouble with commutation. All R and S commute with all R bars. All the operators that they have commute with all of R. This is an outer product of inside and outside. They are independent. Okay, and there's mention of where this started originally. Okay, now, this summing of all of the operators of the group acting on an original state, Euler angle 0 in this case, that's our number one state where we're going to do the Mach-Mach principle as origin. This projection operator has the two indices of the irreducible representation. So what we're doing here is we're just considering all possible positions, indicating that is a ket with alpha, beta, gamma. So those are the position states of the rotor, each of them with an amplitude equal to the irreducible representation star. So this is your e to the minus ikx, if this was a position state x, and k was angular momentum j. Only now it's multidimensional, so I have to do some funny stuff and get a number n, which is being looked at up here. You have to finish this integral in order to get 16 pi squared for this and 8 pi squared for this. This is what you do with R3. You only go from 0 to pi, but SU2 parameter space is twice as big. It's covering this one, so to speak. It goes from minus pi to plus pi. Otherwise, the integrals are the same. I keep the alphas and gammas, they're nice dials. I just integrate 0 to 2 pi on them in both cases. So this one has 8 pi squared, this one has 16 pi squared. That's it. So basically, it's 1 over some sort of normalization. That's the sort, depending on whether you're doing half integer or integer. But here's the picture. Angular momentum is beautifully described by what we call angular momentum cones that we mentioned last time. We're going to go over those again. And these are the laboratory cones with respect to J. J is forced to live very exactly at a certain z component, but also has to have an integer plus a half amount of magnitude. That is, it had exactly j times j plus 1 square root is the length of the angular momentum, quantum angular momentum vector for quantum j. If j is sharp, then that's sharp. Okay? So that forces it out a little bit so that it can fit exactly on a certain value m. And if m is equal to j, it isn't going to just close up and give you nothing. It's going to give you something that's associated with j plus a half. And it's that R cosine is the uncertainty angle, minimum uncertainty angle that we talked about before and we're going to talk about again. That's in the lab. Meanwhile, in the body, this thing is wriggling around with respect to this piece of equipment right here, which causes the piece of equipment to appear to gyrate around J. But the laboratory people see that J, which is star fixed according to the laboratory people, it sees, because of their motion, it sees the J doing a dance around their axis. Which means that their axis can be anywhere in the neighborhood, according to us, of the J with a cone that's perhaps narrower because their n value is higher than our m value. So we can localize our cone and expand theirs by going with n that's smaller. As I make smaller, the cone gets bigger. All this we need to talk about some more. We just very touched on it in the last lecture. Okay, so when we're thinking about the second job of a D function, really the first and only job in most of the group theory books I look at is to transform. Do symmetry transforms of wave functions that are of quantum interest. In particular, do Stern-Gerlach polarization experiments that are manifested by the amplitudes and probabilities that come from the D function when I have a linear combination of the laboratory states, M states, that an operator is going to be able to work with. Now this is now the laboratory operator. You'll see a little bar over on, if and I won't do that very much today. We're just going to do stuff from the lab point of view. But anyway, I want to look at that. And I also want to make sure that you understand the Mach-Mach principle. R of the original state is called alpha, beta, gamma, and we're going to equate that to the body operator, the one that has a bar over it, dagger, inverse. We're taking unitary. That's a little bit of a restriction. I have to change that if this is Lorentz transformations. But just this thing here is the inverse of this, and it will get the same relative state. If you can't, as you can in special relativity, find a definite frame, you see, if you can't nail one particular frame to everyone's satisfaction, then you have to play the relative game, and that's what we're doing here. Okay? So this is true for all alpha, beta, and gamma, and this is true for all alpha prime, beta, and gamma. They all commute. Okay, the inside commutes with the outside, whereas practically none of these commute with each other. And of course, this is the same group multiplication structure. None of these commute with their ilk. So we're going to have a transformation in the laboratory. This is what most people would be talking about, the particular angular momentum state M, okay, and I'm doing a sum over M prime with coefficients. And the coefficients are the Stern-Gerlach amplitudes of a rotated state. But we could have done a body transformation just as well. In that case, we would be summing over these inside guys. Most of the time, people don't see that inside guy at all. They just write this one down. But that's the logical contrapositive of this one. And it's also true that, as I've shown in the picture there, that there's a z component and then there's a z bar component. The z component is an M. The z bar component, most of the time, we're going to use the letter N. Molecular physicists, when they do this, would normally use a K, which is a little bit misleading because K and J are very close to each other, and these aren't close. These M's and N's are equivalent in the relativity back and forth between laboratory and body. In any case, this is the picture I have in mind when I write down these equations. Okay? Now notice the minus sign there. As I say, we normally do little funny things to make that positive, but it really is minus, because if I go and turn the body like that is this way, it's going to see me turning that way. Hence the minus. They are inverse of each other with respect to the original state, the singularity. There's a singularity in all of these definitions. Okay, now let's go through the physics of that transformation. The physics of that transformation, for example, would be to take a spin J, total J, equal to state that has the, not two, but let's just say one quanta of Z component, the subgroup R2 of R3. The subgroup chain at work here. Don't forget that. In any case, I want to take that state that's coming out of an analyzer that has been rotated by beta. That's what I mean. Exits an analyzer that has been rotated. It put that out. Okay, so it's got description by an angular momentum cone that's leaned over by 10 or 20 degrees. Okay, and it's about to go into this thing. And this thing is an analyzer straight up and down. Its quantum numbers are m equal 2 for that output, 1 for that output, 0 for that, you see. So we have spin up, 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 sideways, down, and down, down with respect to this axis. And here comes this thing and has spin up, not up, up, but just up with respect to that axis. And it has to choose which one of these it's going to pick, and it ain't going to be 100% this one. It's given by the D function. The amplitude is here, and the square of that is the probability. So that's what we looked at last time. The overlap of this rotated number one state with all of the unrotated M prime states that we have here, and we have 5 of them to choose from. Okay, 5 channels to spit out something. Okay, so what you're seeing plotted there is the probability, which is the square of the blue thing, which is the amplitude. So this is a case of plotting the irreducible representation matrix M prime n for fixed J, M prime, and n. The quantum numbers are fixed, and the angle is varying from very small, in which case you almost have 100% and exactly 100% if a beta is 0 in the m equal 1 window of the vertical analyzer, because this one is practically vertical if beta is small. As I start to turn it, this drops precipitously. And by the time I've gotten over here to 30 or so degrees, this thing's maxing out, or minimuming out if you look at the phase. And this one over here also getting very excited. But these guys are a little less interested in getting excited. They have second and third order rises. Okay, but as I keep going, making my angle bigger, they'll dominate until finally, if I bring the angle all the way around, if I turn this thing all the way upside down, it's got to come out of this window. So there's 100% right there coming out of the m equal. What did I do there? But made a horrible sun error here. We've got. No, I did. This is the m. This is m prime. I should have called this n. That's the problem. But it's green, so you know it's what I meant. Okay, so here we're plotting for fixed quantum numbers, and there's a whole matrix of these functions. You see, these are all the possibilities. But you see, there aren't 25 really different functions in there. I can see that this guy here on the diagonal at the upper left is very different from this one, is very different from this one, is very different from that one, but it's sort of similar to that one, and these two look very similar, you see. And then as I go across here, okay, well, this one, pretty much different from that one, but also different from that one. A little bit more like that one, but I think what's happened here is we trade 0 and pi. And then finally, this one is the same, so I just shift by pi, you see. So there's really only about 1, 2, 3, 4, 5, 6 really different functions on this thing. And you can go back and look at the matrix and see some of that. But that symmetry of this symmetry is very important. And we're going to be talking about the molecular wave functions from the lab and the body point of view, and it's helpful to have that information at your fingertips, and that's what the computers are good at, is plotting things that way. So this is what you'll get if you plot it on the website. That thing that I showed you there was the old program. This is the new program T.C. Reamer has put together that really shows them very sharply, and now you're not confused by the similarities or dissimilarities that these things have. And then there's the Legendre function right there for P2. Okay. Now, cones. Taking a literal interpretation of the angular momentum relations, namely the z component is m, that ranges from j to minus j, and the actual magnitude is bigger than j by about a half. It's the square root of j times j plus 1. Because of that, even the m equal j level has a little bit of uncertainty in the x and the y directions. If you really demand that it be quantized perfectly with respect to the z-axis, then you have a significant, for low j, uncertainty around. And this is showing you how big that is for angular momentum 20, which is a pretty healthy angular momentum, but it still has a lot of uncertainty if you set the the other quantum number. Let's see if I've got it written here. M equal 20 here. But M equal 19, already with just one change down to 19, this cone has widened up to the next cone here, you see. So what we're talking about are coherent states, in a sense, like the harmonic oscillator has a Gaussian, and there's the sort of Gaussian, but as you come around to close to 90 degrees, you really see its shape is shaping up here, and it only needs a few more degrees to be an absolutely centered Gaussian. So all of the 41 functions, 2 times j plus 1, are all listed. All 41 possibilities here are all listed, and they're all different functions, some of them very different, but you can see that most of them are very zero, you see, here, and here too, but it's getting wider because the cone's getting wider. And the thing that's neat about the cone is its edges point right to the inflection points of this discrete wave, the wave that only has values at integers of the quantum number m prime. So I find this beautiful. Now when this one gets close to 90 degrees, it's making something that looks like the first excited state of what was the ground state, you see. But that interpretation is subject to grain of salt, because it's not a continuous wave. So let's just look at a few of them for j equal 10. Okay, and again we're plotting here this function, same function we've been plotting, but now we have it for fixed beta and the n quantum number. And we're plotting m. Okay? Versus m for fixed here, and now we've got n equal 10 as well as j equal 10. And beta is going to be, for example, 0. Well, we know what that is. It's just 1 for m equal 10 and 0 for everything else. Absolutely. That's the orthogonality relationship there. But just move this thing a little bit, just to raise that angle a little bit, and oh, they're all getting real interested in the neighborhood of the cone. They're in the neighborhood of the cone's vertical drop. Is lots of activity, rest of it 0. And then as I keep going, you see, that thing follows the shadow of the edge of the cone, where the j is presumably everywhere. And then it brings it down here till I get 90 degrees. It's pretty good Gaussian. And then the square of this is being shown there. It really is limited by that shadow. That's the square, of course, you would expect to be smaller, because these things are all less than 1. So I go now with n equal 9, much bigger cone. But at first it doesn't get much bigger shadow than that one does. And so forth as I raise it up until I get something that's, you know, looks like an oscillator, harmonic oscillator. First excited. There's a second excited harmonic oscillator, you see, now with 8 instead of 10, you say. And then 7. Now the cone's getting pretty wide. It's got getting to, so that it can easily cover almost the whole range, but it still is going to have very small values outside of that shadow, the semi-classical shadow. Okay? So, this is a beautiful piece of quantum mechanics that no one looks at, except crazy people like us. Okay?
What determines the wavelengths of, or I can see that when we have bigger projection of the cone,
The edge.
the edge of the cone,
dotted
we
line.
have more fluctuation coming up and coming down.
What you could call it is the classical turning point. That's what you'd call it. And if it was a
What
potential.
determines that length?
Yeah. Inside that you can have wiggle. Outside, exponential decay.
What determines that length? Because I think
This,
no
right
no
here.
no 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 the length of the
Of this.
yeah.
Let's work that out. We've got that worked out. This is just angular momentum 30. 30's got a lot of flare to it. Okay, and it's one we'll use later on for molecules. This is very nice spectra in the 30 region. We'll show some of this stuff. But you can see it's the same thing. It's just now the cone's really narrow, so the Gaussian is really narrow. Let's go ahead and look at the high J properties of this. Okay? What we're interested in is the delta M. And if you believe this literal interpretation of quantum mechanics, which is this has got to be J times J plus 1 square root, this has got to be N, okay? And then I'm going to drop that on a M axis. Okay, I'm going to drop that down, right? So I've got a triangle here that's square root of J plus 1, and then, since this is N, this is square root of J plus 1 minus N squared, right? Pythagorean theorem, right? Okay? And the projection of that is sine beta times 2, because I've got 2, right? If I didn't have the 2 there, I'd just be measuring the half width. I want the whole width. Okay? So that's the thing that can give us a formula for delta M. Pretty cool. Okay? Well, how's it working? Let's take n equal J delta M would then be 2 times the square root of J, okay, sine beta. And we got 45 degrees here, so sine beta is square root of 2 over 2, okay? And I've got 2 times this, okay, that gives me square root of 40, which is about 6.2. So I count here. 1, 2, 3, 4, 5, 6, and a little more. It's working out. Okay? So that's what you can do with this thing. There's a much better picture of this one with 45. And I haven't mastered this program well enough to make it 45.0, but it doesn't make much difference. 2/10. Okay? Now, here's another one. Go to 90 degrees. Okay? Now you're talking 2 times the square root of 20, which is about 9. Same deal. It's very close to what you see. And all we're doing is measuring that shadow with this formula, okay? And there's some examples which I'll let give some problems that you can do. But it's all based on this. Okay, and it works everywhere I've tried it. Even down for low J. But then usually cones are very big. So you don't even have, the shadow goes outside of the M range. Okay, now let's go and look at the wave functions. This is where it really gets spooky, and I'm only going to spend a little bit of time on this because I still don't understand everything that's happening with this. But here we're going to actually plot some of those functions that are off the center. Here's m equal 20, n equals 0. Well, that's kind of on the center. So this is very much like a linear molecule that's just doing its thing with respect to m. I'm not too surprised about what I find when I plot this. If I plot a few more of them, this is the old program right here doing the plotting. And as I go and make m equal 20 and n equal 20, that's very much off the center of the matrix. Okay, I've got 2 cones that are equivalent. Okay, and both of them give me a pretty good estimate of the width of wave functions, 0 in between. You see, and then this one, pretty good. If I put that together, I have something with a node here, so I'm 1 off. You see, then I make m equal 19. Ooh, I get that.
So, quick question, if you don't mind.
Go ahead.
Are the amplitudes here the circles on the other graph?
Say that again.
Are the amplitudes on these graphs the circles on the graphs that we were just looking at?
Are they the circles we were looking at?
Beta is on the horizontal axis in this figure. The previous one, it was discretized.
Yeah, see this one is
So,
not the same plot. Okay? We're back doing wave function now.
but if you take one value of beta on this
Mhm.
graph,
Yes.
does that match up with the circle?
Yes,
that are
it
on
would.
the graph?
It would. We're seeing the effect of those cones. I'm trying to picture the cones from both the laboratory's point of view, which is always a nail to the vertical, and then finding the other cone just by how it tangents to J. That's all that's going on here. That's this picture. But I have to realize that I'm going to be flipping around, if I'm looking at it from the laboratory point of view, or if I'm in the body, I'm going to see this thing flipping around, you see. This is nailed to the stars of the laboratory. This J here is nailed to the stars of the body, but it's not nailed. That's the asymmetry. This is a conserved vector in a classical study of a laboratory rotor. It's fixed to the stars. The rotor is precessing. So that makes it really squirrely. Okay, this is a new program which much better drawings lets us really see what the angular uncertainty is. It just nails us right there. Real, you know, this you can see for small deviations from the total. It's where when you get lower angular momentum, you get more stuff happening. So I'm going to leave this because we're not anywhere near done with understanding this. We need some more work. Okay.
So you don't know why the functions turn out to look like the harmonic oscillator functions?
I have really tried. And somebody named Roy Gordon tried to do it when he discovered stuff like this for the Clebsch-Gordon coefficients. Now what's really funny is everybody in group theory does things ass backwards. The first person to know about this effect was really direct, but Rocca picked up on it, and he found this phenomena with Rocca coefficients. And then Tullio Regge, the guy that does all sorts of weird numerology for high energy physics, explored that. We're the first to look at where it comes from, which is from the D functions. Well, the D functions are the progenitors of the Clebsch-Gordons, which are the progenitors of the Rocca. Let's go back to the birthplace to look at things. So what we're looking at here is birthplace. It's still mysterious in many ways, but a lot less so. So we've made progress by taking things simpler. That's Occam's razor. All right, now the third thing that the D functions do is give you Hamiltonians. Now and dispersion functions and eigenvalues and eigensolutions if things are right are good with the symmetry. Okay, so if you're thinking Fourier analysis, the e to the I kx is the wave function. Star e to the minus I kx, it's a transformation function. It's just a joint to e to the I kx, so that's pretty trivial. Okay, and then the e to the I kx functions are used to make the dispersion functions by Fourier analysis, basically, but sometimes they, just a couple of them does the job, like the cosine wave for the block dispersion function. So that's what we're doing here, only now it's these big groups, R3 and SU2, or just U2, if you want to keep the phase. And it's probably a good idea in this science to keep the phase, baby, and that's what we're doing. The T expansion, multiple expansion of the asymmetric rotor. I will go through the algebra of that, and then I will do the same for the symmetric rotor. That'll be trivial. I'll simply set A equal to B, and we'll look at the rotational energy surfaces of those and get some feeling for some of this behavior that we've been talking about. So anyway, here's our old friend, the D functions, and they're going to give us, first of all, the Legendre polynomial. Okay, but I want not just the dimensionless guys. I'm going to go ahead and leave the R squares here. So this is really an XLM, or XKQ, that we're writing out here. Okay, and it's a polynomial in X, Y, and Z. So that's what these functions are good at giving us, the multiple functions of X, Y, and Z. And there's the first one. Now what we're going to do is we're going to replace every x and y and z in there with angular momentum operator. For example, I could use linear momentum. That would be okay. Any vector, it's going to work, because that's what these things have the same symmetry properties with respect to rotations anyway. So I'm going to call this, just because this is x20, I'm going to call this big T20. And there it is, combination of z squared minus x squared minus y squared with z squared multiplied by 2. Okay. Another way to write it is this way. That's total magnitude j squared times 3 cosine squared theta minus 1. That's the Legendre polynomial, p2 cosine theta. Okay? Just to, try every different notation I possibly can think of. Then I'm going to take the extremal states, 2 plus 2, and 2 minus 2, this guy and this guy, okay? Make that little binomial right there, and add them up. Okay? If I add them up, I get a thing that looks like that. X squared minus y squared is what I get for polynomial. Okay? There's the polar coordinate equivalent of it, r squared times cosine 2 phi sine squared theta. Well, I'm going to write that out too, just like I wrote this one out. Okay? Now, this is not just a simple Legendre polynomial. This is one of the associated Legendre polynomials. This is perhaps a name that you might find in a textbook somewhere. Okay? So there we go. We got the extremal states, plus and minus 2. And then we might as well do the difference while we're at it. Okay? Well, what you get here are the cross terms. I just put a setter here, there's 2 more of them. Okay, remember the guys that avoided all axes? And then don't forget to scale it. Okay? So what we're going to do is we're going to put these guys together. Particularly interested in this one, this one. Okay? They're the ones that love axes, and that's what we want. I'm not so interested in dipole now, because that makes a very funny rotor, and we'll talk about that later on. That's a thing that has parity minus. You can see the inversion puts a minus on this. But we do want this one. This one's parity plus, and that one's parity plus as well. It's a United state with a positive 1 of the inversion. So what I'm going to do is I'm going to put these guys together to make the rotor, to make this rotor. Okay? Now, we don't need these guys. These are cross terms. If you were to put your rotor Hamiltonian in an arbitrary basis, then you would have cross terms in the matrix. You wouldn't just have a diagonal x squared, y squared, and z squared. You'd have the other possibilities. So we don't need those for what we're doing. So here I'm just playing with this thing right here, but I want to point out that these coefficients, A, B, and C, are inverse inertia of, respectively, the x-axis, y-axis, and z-axis if I line up A, B, and C that way. And I often do put the circular guy on the z-axis, because most of the time we are doing complex Coriolis, curly, centrifugal stuff. But right now I'm just going to say, okay, how can I make this into these guys? So I'm just going to go something that adds up to 1 here, okay? A third and a half minus a sixth, or third minus a sixth plus a half. That would give me the A. You say jx squared, okay? If I put the minus here on that thing, adds up. Okay, and I do the same with the next one, okay? But now I got to put a minus here because of that one, okay? And then here I don't have to worry about this one at all, but I do have to put a plus 1 and a plus 2. Okay, so that's what I do with the 1/3 and 1/6 and 1/2. Okay, and now it'll add up. Okay, so I'll get a coefficient here of this one. That's just a sum over 3 of the 3 parameters, and then I'll get this minus A minus B plus 2 times C, again divided by 3 of these things. Okay, that's this thing. And then finally this guy right here, that's the one that's going to make it asymmetric. So there's the thing that I want, is the Hamiltonian written out as a sum of those 3 tensors. and I don't need the T2 ones or the odd parity with a minus sign there. That was the XZ. I'm sorry, was the XY cross term. So that's the asymmetric top Hamiltonian written out in terms of these tensors that we get from the d functions of angular momentum 2. Resulting is a semi-classical asymmetric top expansion. And this is the asymmetry term. A minus B, if they're equal, I don't have any of that. I just have a Legendre polynomial. And some extra, radius. That's the scalar part here. And this is the tensor part. There's the asymmetric tensor part right there. So that's the general case of a rigid rotor with these inertial coefficients. And here's the one we can look at first because it's really simple, and we've already solved this one way. This particular thing right here comes out to be j squared b c minus b over 3 cosine theta. That's what the thing would look like if you just write it out as a function of angle. Okay. That's what I call semi-classical. And we can get away with that usually. Anyway, there's one way to look at it. There's another way to look at it. Jz being j cosine. So, okay, let's look at a thing called the rotational energy surface. What I'm going to do is I'm going to plot this Hamiltonian. Bj squared c minus b. Okay, and I guess I left out the what those were, but these are inverse inertia associated with, first of all, the z-axis, and then b is x or y. They're both equal. Okay, so eigenvalues for this would be, we already know, j times j plus 1. And then this jz squared here, if you say jz squared is a magnitude cosine theta, and let the magnitude be literal interpretation of quantum angular momentum, all right, then I can write that this way or this way, where I use the angle of the angular momentum cone. So I plot the Legendre polynomial, okay, and then I put cones through it. And where those cones hit the surface is exactly giving me the eigenvalues we got by just doing the simple quantum mechanics we did in the last lecture. That's cool. So there's the uncertainty angle, k over the square root. You put that in, and you get exactly the eigenvalues. As the radius, you see, the energy is being plotted radially for a fixed angular momentum j. And that's the cool thing about this, is if a free-flying molecule, total angular momentum not going to be changed. No torques crank the energy in the angular sense. Okay, so that's kind of cool. And now what I'd like to do is look at the levels. Okay, now here's the kinetic energy coefficients we really need. I've got the x bar and the y bar in the body frame of this thing. Okay, it could look like that, or it might look like a frisbee or a discus. This is called oblate, this is called prolate. I've got those equal. Then I've got A is different. Okay, the one that's got the z inertia in the denominator is either bigger or smaller. In this case, it's smaller. Okay. So this corresponds to A greater than B, A greater than these two equal numbers. And then this one is A less than those two. If it's a discus, A will be about a half of these. That's a theorem of, it goes back to the Greeks. More or less. They obviously didn't do inertias, but they did the geometry that it takes to calculate them. Now, this is our formula, and right now every one of these j levels here, j equals 0, j equals 1, j equals 2, j equals 3, has Mach multiplicity. That is 2j plus 1 squared. Okay, but you're only seeing the 2j plus 1 on the diagram here. For j equal 1, well, for 0 you're seeing 1, big deal. But j equal 1, you're seeing a triplet, it's just that 2 of them are degenerate, n equal plus or minus 1. And then for j equal 2, you're seeing 5 levels. And then n equals 0, and then a doubly degenerate like this one had. And then another one, just a little bit further down, it's quadratic, you see. It's quadratic in n squared, and with a minus sign for this case where a is less than b. So as we go more and more angular momentum, the energy drops for this one. Whereas for a bowling pin, elongated symmetric in azimuthal direction top, like that, okay, you will go up as you make more and more n. So that's what we're getting from this formula. It's rather amusing and beautiful. But the thing to realize is that even the n equals 0 levels are also 2j plus 1 fold degenerate, and I'm not showing the degeneracy. So each of these levels that are indicated, all 3 of them, have 3 levels of their own, making 9. And each of these have 5 levels of their own. This one has 2 5s, which makes 10, and this is another 10, you see. And then 5 right there. So that makes 25, the square of 2j plus 1, where j is 2. And so forth as we go up. So the thing that people are not familiar with is this internal quantum number of a molecule giving us this beautiful set of rotational levels. And what is sort of neat is, of course, that for j equal 10, which would be way the heck up there, that's the way you lay out the actual energy levels in for a single j, in this case j equal 10. Okay? And here's where they go if the inertia of the z-axis goes to 0. If you're talking about a diatomic molecule where the inertia on the z-axis is nothing or is astronomically small because it's just a nucleus of some kind, like O2 or N2, okay, it's got oxygen nucleus, it's a tiny inertia. It has let its energy essentially go to infinity. It's gone into another field called nuclear physics. It's gone into millions of electron volts instead of just fractions of electron volts. So all of the non-zero levels gone. They're not here in the molecular physicist world. N equals 0 still here, n equals 0 still here, n equals, you only get to use n equals 0. So there is no body structure to speak of for rotation. It's called nuclear physics when it happens. So this is something to be aware of. This is why people forget about n. Because most people only study up to diatomic, and they just think they're doing ordinary angular momentum calculus here, but they're not. There's 2 sides to this thing. And boy, another molecule will show you that very quickly. So here's the rotational energy surface drawn in 3D, the way we did it at Los Alamos quite a few years ago, showing a constant energy sphere intersecting a set of levels. It's j equal 10, just like that one. You see the same levels on there, but they're colored according to symmetry, we're going to talk about in the next lecture. This is the rotational energy surface for the case that we have here, A less than B. Here you start on the equator and go down in energy. Here you start on the equator and go up in radius. Very different. Very different figure. It's a tire. And the thing about rotational energy surfaces is the surface itself has the same aspect as the object itself. And the diatomic molecule would just be this thing to infinity. All of the surface is all the way to infinity in radius. It's just like that. Looks like a singularity blossoming. Okay, now what I would like to do is get you more familiar with the energy surfaces, rotational surfaces, and I want to introduce the asymmetric rotors and show a little bit of its energy levels. And then I want to come and give some context for the next two lectures that we're going to be doing after this one. So here is the J equal 10 case that we did in some detail, here's the J equal 10, using the same cones. Where they intersect that surface, that's where the trajectory of J really is. And that's the other thing that you need. Now here's an asymmetric top. It's halfway between this one and this one. There are the little rings around this one, and there are the little rings around this one. That's what you get when you plot it. That's really cool. And that's a, you know, you take an object like this eraser here, and that would be the rotational energy surface for that eraser, more or less. Notice this place right here, where you cannot rotate the eraser without having it turn over. If you've studied classical mechanics, you know that. We have a little demonstration that we can show, perhaps, if there's time, of that. The best way that I know to show it is do the water molecule, which would be sitting there on this diagram. That would be the water molecule. It's got a bend to it, you see. And it's got a very high kinetic energy around this thing for a given amount of angular momentum. You really have to go fast around that axis to get angular momentum J equal 10 in these units. And then this is a valley that corresponds to this thing flying like a boomerang. So this molecule is quite stable, flying like a boomerang, really stable because it's the lowest point it can do, keeping its total angular momentum constant. This one up here, okay, also is stable. I can throw this thing in the air pretty carelessly, and you can see that it's behaving. It's just maybe processing a little bit around that axis, but you can't see it. But try to do this. That's really hard. Okay? And I'll try to do it best I can. I don't know if you saw that. It flipped. Okay? That was a lousy throw. But you see it goes back and forth.
Yep.
That was a lousy throw, so it was back and forth almost instantly. I was probably up here on that trajectory. I'm trying to get it right in that neighborhood, you see. If I could get it exactly in the neighborhood, it would go forever. Well, not forever. Did you see it flip there? Mm-hmm. Yeah. So this is something. That was another flip. Do it with a tennis racket. Try to make a tennis racket go end over end without turning. Bet somebody that they can't do it and you'll win. Okay? So if you're just slightly bit off there, you hang there for a while, then you go zooming around, and there's a picture that shows, you basically use the left-hand rule here to show where they're going. Those are the arrows for the trajectories of the angular momentum vector, which is fixed to the stars, but in the body frame it's all over the place, depending on where you are on those curves. Now later on we're going to use the D2 eigenvalue symmetry to sort the actual quantum values of this thing, and we will be looking at pictures like this, which show you where the separatrix is, and we'll be looking at the actual spectrum of J equal 10 labeled completely. This is in the Springer Handbook of Atomic Molecular Optical Physics. We'll talk about that next time. What I want to do now is just set a context for this, and we only have about 10 minutes left here to stay within our usual time for a lecture, an hour and 25. What I want to do is just do a sketch of modern molecular spectroscopy, remind you of the spectral quantities, terahertz, 100 terahertz is in near infrared, 600 terahertz is a beautiful blue-green, but then come down, gigahertz, that's I should say gigahertz, it is the in unit for computer clock times now. They're trying to get them up to the terahertz, and they may succeed in a fairly short period. It used to be they ran at megahertz, and we were really impressed with that. Kilohertz was the radio frequency that the very first digital computers would operate at. The wavelengths that go with these things, okay, femtometers, picometers, nanometers, microns, millimeters, centimeters, kilometers, okay, that's wavelength measurements, and that's a perfectly good way to describe the spectra that's coming out from, say, an electronic manifold. This would be like a Rydberg series for hydrogen, but it's not too different in its higher regions for the highly excited electronic states of any molecule or ion. The alpha, Lyman alpha of hydrogen is ultraviolet. It's running at 2.4 petahertz. Okay, that's the next one after that one. Okay, the energy is 10.2 electron volts. That's a lambda of 125 nanometers. So these are all units that worthwhile getting used to them, particularly as we go across the spectrum into the high resolution region, where we're talking about finer motions than a really fast electron vibration that I'm indicating there in that spectrum, that sort of hydrogen-like spectrum. But if it's a molecule, it's going to have vibrations, and if it's a solid, it's going to have phonons, as well as the excitons, and all of the stuff that those two can do together are all part of the game. But a molecule, you see, can do this. So we have both electronic motion, ion vibration, and our third thing, we've got rotation that I've been sort of showing here. So the real base of our quantum mechanics for high resolution is on the rotational end. But the thing is, you see, every one of these electronic states of a molecule is going to have at least, and this would be true for H2, where we would have one vibrational manifold on top of each electronic state. And you blow any one of these up, and for a while it'll be like a harmonic oscillator. And now you'll be talking about typically 30 terahertz, a lambda of 10 microns. Okay, for CO2, that's a very famous vibration in CO2. Okay, it has a wavelength of 1,000 waves per centimeter. That's centimeter inverse. And the EV, electron volts, it's a tenth. I should say 1.124 electron volts is a 10 micron thing. So, you know, you do this enough times, you start, even I, with my Terrell memory, I can get used to some of these units and be able to talk to people in different fields. And every field uses a different region somewhere, you see. So it's good practice to be able to talk across the physics spectrum, so to speak. Next stop is rotation. Wow. Microwave is what you're talking about there. This is what heats up your popcorn. When you heat the water, you get it rotating. You're cranking it up with these resonances here. And what I'm talking about always is differences, you see. Always differences. Those are the spectra that are coming out for these various motions, you see. So this is the region. When you have both of these things going at once, it's called vibronic. That's a vibration electronic. When vibration and the rotation is going, we call that rho vibrational. When everything's going, it's called rho vibronic. Okay, so just to get you the terminology right. And then it gets finer than that after that. Typically, nuclear spin hyperfine splittings will be some tiny fraction of this. They can be kilohertz. Okay, this is megahertz, typically fractions of kilohertz. If the moments aren't too very big. Ammonia, doublet. Okay, that's in the gigahertz. 24 actually for the average. But there's a whole bunch of them. That's the thing. Every one of these levels has got a doublet. That's what makes it complicated. And then the stuff we're going to talk about is the precessional tunneling, the superfine splitting. Remember our little cluster A1, T1, E? Those things can vary over 15 orders of magnitude with no problem at all, in the same multiplet of the same molecule. So they're the ones that you really can do things with if we have ways to control them. So what I'd like to show you real quick here is the spectra, the way we would display it if we were actually trying to analyze a CO2 10 micron band, okay? What we would do is we would put the energy levels for the initial ground configuration, and it wouldn't necessarily be the ground. It might, you're going to be thermally distributing over many J. With big molecules, you'd be over J equal 150 is no problem. Which CO2 goes up to J equal 20 easily. We can see stuff there. And then we're going to excite to one quantum of vibration also having its J values. And then what you do, and this is something that I did in that Reviews of Modern Physics thing in 1970s, was I said, hey, I cannot visualize energy levels and just draw lines between them. Those are called Grothian diagrams, and they're absolutely useless. What we want to do is we want to see actually where the spectra are, because we need a geometrical way to take a difference, and that's what this is doing. For instance, this one right here points, if you do a 45-degree line, to that particular spectral line. That is a transition, you see, and I'll just point to both places. That one right there, P4, okay, is a transition from the ground state J equal 4 to the excited vibrational state nu equal 1 instead of 0, and J equal 3. And P means the Latin plummet. I'm just making this up, but that's a perfectly good way to remember what happened here. The angular momentum went from 4 to 3. Okay? Now the other possibility is that the angular momentum didn't change. That's Q. Q stands for status quo. I'm making that up too, but that's the way I remember things. Terrible memory, see, so I got to do this. Okay? And then, this is easy. This one raised the angular momentum. Okay? R4 started at 4 and went to 5. Okay, so that's a little matrix, you see, of all the transitions that you could possibly have just displayed for you. And it's a dipole transition, so we don't go outside of plus and minus 1. But if it was Raman, you would go with 2s, and you'd have other letters here, P, Q, R, S, okay? And you'd have O, if you want. I've seen that, but it's certainly possible. So here's a way for you to see the dipole transitions. And this is a kind of spectrum that's up on the wall there for a number of molecules, including some really big ones. Now, I want you to point out something really quickly here. This is what doesn't work. If I were to take my rotor energy to be B times J squared instead of B times J plus 1, which I did do here, if I do that and I put all my transitions, it doesn't make sense at all. I don't get the even spacing. You must use J times J plus 1, not J squared. Okay, so if you're teaching elementary modern physics, that's a good way to show the angular momentum cones are not, we're not just kidding about them. The experiment says that's what we're doing, okay? Now, as I said, there's a vibrational transition which blows up to that. There's your P, Q, and R branch of a very complicated molecule, tetrafluorosilane, which is part of our ozone mysteries. When we were having our ozone layer destroyed, Freon 14 was one of the culprits. And knowing this spectrum helped a little bit. You can read about this in 96, Handbook of Physics. Here is the same thing, 2005, and I suspect when they do it again, we're going to just make the figure more and more fancy. Maybe we'll have something else to add by that time. Okay, now, I think I'm going to quit here because this is what we're going to do next. We're going to actually work out the matrix elements in body and lab, but mostly the body. That's this one right here. Very similar to the lab. There are the things that we wrote down, square root of J minus M, J plus M plus 1. Remember the AA daggers gave us those very easily. So we're going to use them. We're going to make a matrix out of those, okay, for each of the angular momentum operators squared, which is part of the rotor Hamiltonian. So we're going to take the rotor Hamiltonian apart and literally write down its matrix elements and make matrices like this. And then we're going to put that on a rotational energy surface, see where it lies, do some fun stuff with that. Then we're going to take on some bigger molecules. So I think at this point we probably haven't burned up our battery or our memory. We should bid adieu and wish you a good weekend and see you next week.